All right. Let me go.
Okay, I think we can get started. So our final talk of the session is Daniel, who will be telling us about how nice is this functor, please.
Great. Thanks. So typically, I think I'd say I'm happy to be here, but I have to say I'm unhappy to not be there. I broke my foot last week, so it kind of interfered with the travel plans. Right. So let's launch into it. This is joint work with Ben Bumpus, James Fairbanks, Fab Genovese, and Caterina Puca. So I'm gonna do things somewhat backwards and throw you straight into applications before building up the theory that helps us make sense of some of them. So in the initial slides, I'll go a little fast and loose, and then after introducing the theory in the middle sections, we'll return to the example applications and pay more attention to details. But so to start, let's think a little bit about Petri net. So consider the following Petri net, and recall that a Petri net just consists of places, which we draw as circles, and transitions drawn as boxes, and then you have directed edges or arcs going from places to transitions and from transitions to places. So to be a bit more concrete, this might represent the action at a barbershop. You've got some customers waiting in the first place. You've got some barber chairs that can be occupied. And you've got in the second place, and you've got some barbershop employees that are free or available to cut hair. And these two transitions of serving customers and finishing cutting and getting sent back to being an available employee. So yeah, as is typical, we then place dots called tokens in the places, moving them around using the transitions. So for instance, the marking on the left becomes upon firing T1 here, this particular marking on the right. So yeah, just to get a feel for these, probably most people in the audience already know all about Petri nets, but in case you don't think about them very much, this is the sort of thing that would be involved in an execution of the net, ending up with three, from the initial marking, we then end up with three barbershop employees that are available, but there are no customers left to serve, so it halts there. So sometimes we want to distinguish between individual tokens, though. So we consider colored nets or guarded nets, which you can think of as defining sets of colors to places, as depicted here, and transition guards to transitions. So in a bit more detail, with these colored nets, you have tokens that get endowed with colors or attributes, depending on the place of the token. And each arc is decorated with an expression that modifies the token's attributes as they flow through the net. And each transition is decorated with a predicate and only fires on tokens whose attributes satisfy the predicate. So going back to just this picture, you might think then of the blue dots over the first place as like rich customers, and the red as poor customers. You might think of pink as an expensive barber, the gray as moderately priced barbers, and the black as the owner of the barbershop, who is indeed a barbershop employee but doesn't cut hair. And you might think of the green as like a fancy barbershop station or chair, and the yellow as just a regular chair. So S1 then here would be like saying the customer is one of the rich ones, the barber shop employee is the expensive barber, and they're sent to the fancy chair. So now, again, I'm going to go through these first slides to build the motivation a bit fast and loose, and we'll come back to the details after building the theory. But basically, we can convert this guarded or colored net back into a classical net by first assigning a subplace to each color. So for the thing that we've been focusing on so far, this is what it would look like, and a distinct transition box for each of the expressions in the transition guards. So just to give a sense of then what an execution would look like, this is an example here where it triggers twice and then ends up in this state and can't trigger again. So to make the motivation now a bit clearer, I want to consider two things about this first example. So first, consider the green place. Essentially, here there's an obstruction of sorts because you have the same fancy chair can have sent to it multiple customer barber pairs. So looking ahead, we can frame this as a violation of or obstruction to the uniqueness condition required for being a discrete vibration. And now for the second observation, consider the yellow place. So here there's another obstruction where there's this yellow chair type from which we release an employee back into the pool of available barbershop employees, even when there's no customer whose hair they could have been cutting at that chair. So this suggests, now just giving like an to this suggests the barber was released from their station at that chair without ever having served any customer. So this might be something to flag, as many barbers or maybe barbers get paid whenever they get sent back from a chair into the pool of available employees. But we only want to pay barbers that actually have cut a customer's hair. So looking ahead, we could frame this as a violation of the existence condition in being a discrete vibration. So just for one more motivation from the applications, another question that arises for Petri nets brings us to bounded nets, for which we can isolate similar sorts of obstructions. So in these settings, we want to establish when a given Petri net is bounded, and that just means that starting from a given marking, no place will hold more than a predetermined number of tokens throughout any possible firing. So classically, we can turn a net into a bounded net by essentially doubling up the places, adding what we call anti-places. So these are going to keep track of how many tokens we can still add to the place, and then editing transitions so that each input or output from or to a place is now paired with a corresponding output or input to or from the corresponding anti-place. So just to say all that with a picture instead, suppose we start with a simple net. So this is like a simplified a partial version of the example we saw before. Maybe we've got like free or available barbers who can start cutting hair, and then they can finish cutting hair and go back to being available to cut again. So we could construct a bounded net here by taking the places and doubling up with anti-places, which I'll depict in purple, and then adding these new arcs from transitions, turning things around. So if I have 3 tokens here in this overline F, so the anti-place, that's the notation for that, that just means 3 more tokens can be added to F. So there are 3 more barbers that can cut hair, let's say. The idea then is that transitions consuming tokens from a place add tokens to their corresponding anti-place, and transitions outputting tokens into a place need to consume equivalent amount of tokens from the anti-place. So consider this original net for which we might have a particular execution that really can be written down in 2 equivalent ways because the semantics here is fundamentally commutative. Here especially, I think it will make more sense to once we've gotten to the finer details of things. But essentially, at this base net level, we can think about writing this particular execution in 2 equivalent ways. So the way to maybe think about this, if again, this is moving quickly for you, is like a barber maybe only gets paid when they end a haircutting. So that's the E. And the owner balance sheet like doesn't see the difference between the different ways of writing the execution because money is just debited once. So the idea, though, to motivate in a somewhat fast and loose way for now, this idea of there being an obstruction here is like as follows. The equality that I just exhibited is not lifted to the bounded net up top on account essentially of the doubled places. So where we could exchange any place C with itself down below using commutativity, we can't do the same up above with the place and its corresponding anti-place because these are considered different generators and cannot be swapped one for the other. So in terms of the idea, these obstructions witness histories that should morally be identified in the category of executions of the bounded net, but they're not. So again, for interpretation, for the example we've been looking at, the idea is keeping track of bounds on resources like free or available barbers and barbers that are cutting hair or on the job the owner must now regard as distinct histories that really ought to be identified, let's say, again, from like a balance sheet or payment perspective. So these could be considered imperfections of the bounding technique. So these two examples, the colored nets and bounded nets, are just a few of the applications where we're interested in qualifying obstructions, and in particular, qualifying obstructions to a variety of properties a functor may satisfy. So our paper was basically about developing or leveraging some straightforward theory, just a few more or less established facts to qualify obstructions to different properties a functor may satisfy and apply homology directly to the categorical setting. So using tools borrowed from homology, we'll be able to measure how much a functor fails to be something, in particular a discrete vibration or discrete op vibration, or a pseudo functor, depending on context. So in terms of idea, this refines the intuition that topological holes and obstructions to category theoretic compositionality should be regarded as two sides of the same coin. And this falls in line with the thought that compositionality should really be understood as involving a spectrum of distinct context-dependent nuances. All right, so let's look at the basic setup for the theory here and make some first observations. So given a category, we can always consider the following diagram. This really arises by taking the nerve, and here you can just imagine that we're dealing with a diagram of sets and functions. So C0 represents the objects of C, C1 represents its morphisms, Cn represents n tuples of morphisms with matching codomain and domain. So for a particular generic element of C2, you could have an arrow F from A to B and an arrow from B to C. So of course, just unpacking the pieces a bit, the two maps from C1 to C0, just pick out the source and target of your morphism. This arrow from C2 to C1 sends a generic pair of compatible morphisms to the single morphism, they're composite. And the two morphisms from C3 to C2 consist of triples of composable morphisms, and then these two maps compose on the left and compose on the right, take them to a pair of morphisms where the pair on the left got composed or the pair on the right got composed. So yeah, we could keep going with this, but really, if you stare at this diagram, you can find a few obvious facts by considering the commutativity of the various pieces, but nothing stands out of great interest. But you do get something, you could say, more interesting when we put two of these diagrams together. So given a functor, f from C to D, we can consider, and we've now just essentially pasted two of these together, one on top and one on the bottom. And now we have the functor where it's decomposed into Fn. So F0 is just F defined on the objects, F1 is F defined on morphisms, and any other Fn acts on the n tuples by just applying F1 component-wise. So the purpose of our paper was to focus on these squares, and in particular on the two rightmost ones, as well as the middle square, to say things about F. So let's look first at the rightmost squares. So decoupling things, this really actually consists of two different squares, the one involving the source maps on the left and the one involving the target maps on the right. And since functors preserve source and target of morphisms, it follows that if F is indeed a functor, then the two squares above commute. But there's more. So here, I'll just have you recall the definition of a discrete vibration. So this is essentially just a functor with a lifting property with respect to morphisms in the target category, whose whose codomains are strictly in the image of the functor. So yeah, the dual notion discrete op vibration, functors that have a unique lifting of morphisms with a specified domain. So the first proposition says that for f a functor from C to D, then the right square, the one involving the target, is a pullback square if and only if f is a discrete fibration. And similarly, the left square is a pullback if and only if f is discrete op fibration. So the content of the first idea we have is that the content of proposition 1 can be refined. Indeed, one can qualify how much f fails to be a discrete vibration or discrete op vibration. So to see this, let's first rewrite the diagrams in, well, we'll focus on the one on the left, but we can make the same sort of argument with the other one. And we can rewrite them as follows. And since if f is a functor, these diagrams commute. And then we're going to apply the left adjoint to them, which means replacing all sets with the abelian groups freely generated by them, and all functions with the corresponding homomorphisms. And homomorphisms can be summed and inverted pointwise, so we can rewrite those diagrams as follows. And the original diagram commutes, so this first arrow involving the source and F1 equalizes the other two arrows, so the composition evaluates to 0, implying that the image of the first is in the kernel of the second. And that puts us in homology land, and we can define these homology groups for discrete vibrations and discrete op vibrations. So these groups provide a qualitative description of the obstructions for the diagrams in equation 1 being a pullback. And when they're trivial, of course, there are no obstructions. So together with proposition 1, we get that for a functor, the h-1 and h0 for fib are trivial if and only if f is a discrete vibration, and similarly for op vibrations. The proof is essentially by the definition of equalizer. So let's go now to the middle square. This is the more interesting one for our endeavor. So just unpacking it a little bit, it takes a pair of morphisms that are compatible, f from A to B, B from B to C, and maps them going right down into f acting on their composite in C. But it also, going down right, maps them into f acting on f composed now in D with f acting on G. So of course, the square commutativity here states the familiar condition of preservation of composition by a functor. So more to the point, we can relate the pullbacks in the right squares to the pullbacks in the middle square. So if our third proposition says if either of the squares in equation 1 is a pullback, then the following is also a pullback. But what does it mean for a square to be, this middle square to be a pullback? So just as with discrete vibrations or op vibrations, this corresponds to a well-known concept. So, right, the Condorcet vibration, essentially an exponentiable functor. So this is equivalent to a certain factorization lifting property. And when we look at the discrete Condorcet functors, these form common generalization of discrete vibrations and discrete op vibrations. So in a way, it's very similar to proposition 1. We can prove the following. Let f be a functor, then the middle square is a pullback square if and only if f is a discrete Condorcet functor. And then putting together our first proposition, the third, and the fourth, we recover the well-known fact that discrete Condorcet vibrations include all discrete vibrations and op vibrations. But more to the point, as earlier with vibrations and op vibrations, when the middle square is not a pullback, we want to investigate how far a functor is from being a discrete Condorcet vibration. So again, we can do a similar sort of thing to what we did before and define these discrete Condorcet vibration homology groups. So in a way similar to proposition 2 as well, we can then show that h-1 of Condorcet and h0 are trivial if and only if f is a discrete Condorcet functor. So these groups essentially give us a way of measuring obstructions to being a discrete Condorcet functor. All right, so now we're going to come back to the applications that we started with. So as suggested by the opening slides, one application comes in the context of categorical semantics for Petri nets. To apply our ideas, we'll start to be a little bit more precise about how to think about Petri nets and their semantics categorically. It's well known, probably especially at ACT, that the different kinds of Petri net freely generates a monoidal category of an appropriate sort by essentially using its places to generate a monoid of objects and using transition as a generating morphism, with domain and codomain the monoidal product of its input-output places. So a marking of the net then, or a way of placing tokens throughout the net, then corresponds to an object in the monoidal category, and an execution or a firing sequence that is a sequence of transitions carrying markings to other markings will correspond to a morphism. So to visualize this, we'll make use of wiring diagrams to display morphisms of the monoidal category, which would correspond to executions of the net. So here, just focusing, let's say, on V, this is up above the net, right? So it has a transition with V, and the input places come from P2, but then it can go to place P3 or P4. So we're going to really work with kind of two categories of interest. So given a Petri net, we'll talk about the free symmetric strict monoidal category, Fn, the category of executions of n. So where the free monoid of objects is just the set of strings generated by P, with unit the empty string, monoidal product given by string concatenation. And then morphisms are generated by the set of transitions, essentially. So on the other hand, we can also generate from a net the free commutative strict monoidal category Cn by considering the free commutative monoid of objects from using the places, and empty multiset as unit and multiset sum as multiplication. So the idea here, though, is that the correspondence between Petri nets and free strict symmetric monoidal categories supplies a process semantics for a net. And the difference between the two things I just mentioned, Fn and Cn, is that the semantics Fn distinguishes between tokens living in the same place, whereas Cn does not. So part of the utility of this execution semantics is that it lets us interface with other structures using monoidal functors. Categorically, though, when we have an extension like this, as we find with guarded colored nets or bounded nets, these are described by endowing a net n with some sort of functor, Fn to D, or depending on the choice of token philosophy, it may be Cn to D. And in practice, D is often taken to be span, but it could also be set with partial functions. And the functor is usually denoted n sharp. So guarded nets can be with side effects, really, meaning there's some non-determinism. These can be described as nets endowed with strict monoidal functors, Fn to span, and bounded nets as lax monoidal functors from Cn to span. So now we're starting to arrive at how we can make use of our earlier results to bear on such things. So to apply our results to Petri nets, we need to use one fact. So fix any lax double functor from the double category B to span is a pseudo functor if and only if the projection of its growth and deconstruction is a discrete Condorcet functor. So as a corollary for any lax double functor, F, the groups this H-1 of Cond and H0 of Cond measure obstructions to pseudo functoriality of F. So thanks to this lemma and corollary, we can measure how far a categorical decoration n sharp from Fn to span or n sharp from Cn to span for a Petri net is from being pseudo. And we would do that by examining the homology groups of the associated growth and deconstruction functor. So what meaning does that have from the Petri net point of view? To see this, we'll want to internalize the guard semantics and first, let's say, the free category Fn associated to the n, net n. And that means we're associating a traditional unguarded Petri net M such that it has the same executions. So given a net n and a functor n sharp, the process of internalization is described by taking its growth and deconstruction. And this gives us a way to internalize span semantics to nets. But in practice, it just means promoting token colors to places and arcs between token colors to transitions. So let's sum this up with a picture. This is an example that kind of simplifies the one from the beginning. So for the picture on the left, we're decorating a base net N with token colors and transition guards by defining a strict monoidal functor N sharp from Fn to span. Since Fn is freely generated, this amounts to mapping each place to a set of colors and each transition to a span, representing how colors are correlated by transitions. But then for the picture on the right, internalizing, we obtain a net M such that its category of executions is the internalization of N sharp. And in practice, again, this means promoting token colors and arcs in the left picture to places and subplaces and transitions. So we know that the functor N sharp for guarded nets is always strict. So the associated functor pi from the Groton deconstruction is always discrete conjugate. However, it's not always a discrete fibration. So take, for instance, the leftmost transition in the other underlying net and focus on the left, on the yellow place in the integral of N sharp. So the discrete fibration condition requires a transition leading into it, but we don't have one. So we have the failure of existence. And in the case of the green place, we have more than one. So we have failure of uniqueness. So the green circle place would be picked up as a non-trivial element of the homology group H-1, and the yellow place would be picked up as a non-trivial element of the homology group H0. And then altogether, these groups would give us qualitative information about which token colors are problematic with respect to the discrete fibration condition failing. So quickly, I'll just go through the bounded nets and then mention one more and wrap up. So another interesting case is that a bounded nets, and here our semantics is lax monoidal from Cn to span. And again, the semantics is internalizable. So our functor, though, is only lax. So the lemma tells us that the functor, this pi functor, is not always discrete conjugate. So the way to think about this is in reference to this picture here. So for the base net N, we have a particular execution that can be written in two equivalent ways because we're using commutative semantics. And this execution, seen as a morphism of Cn, corresponds to two different executions of the new net M, which are in turn morphisms of the category of executions of M, or the internalization of N sharp. And the reason, though, why this equality is not lifted kind of upstairs to the picture on top is that in M, all the places of N get doubled. So we could, at bottom, exchange any place C with itself, but we can't do the same up top because again, as we mentioned at the outset, the place and anti-place corresponding to C, for instance, are considered different generators and can't be swapped. So again, the idea is that the obstructions to being discrete conjugate would witness histories that morally ought to be identified in the category of executions of this bounded net, but are not. And again, the homology groups would give us qualitative information about these obstructions. In particular, the example we have here gives us a non-trivial element of the H-1 group. So very briefly, one other example we considered was to delta lenses. I'm kind of we'll go through this very quickly. So the one way the concept of lens has been formalized is via the one that we're interested in is via delta lenses. So instead of defining it, we'll just note that delta lenses generalize the concept of op fibration, and the lift here that we have is not guaranteed to be unique. But we can say essentially by using our techniques that we can measure how much a given delta lens fails to be a discrete op fibration. So H0 will always be trivial, but H-1 is generally not trivial and measures basically how far we are from having unique lift operation. So the application of this is that a delta lens is kind of, that's also a discrete op fibration, is a pretty rigid structure. It tells us that there's only one way to push an update of the part to the whole. But being a discrete op fibration then means that the structure describing the way a part is transformed canonically induces a transformation structure for the whole. So it's a pretty sensible thing to want to consider obstructions to delta lenses being a discrete op fibration. So yeah, just very briefly then, wrapping up, the idea here is that investigating failures of compositionality has the potential to impact several real-world applications, especially in ML systems. And formal techniques to qualify such obstructions may hold promise in improving understanding of machine learning's inner workings. So another maybe important question is, what about the further squares to the left? And one conjecture could be that if you look at the diagram, the next square proceeding to the left could be used to measure the laxity of a given functor without necessarily going through the corollary from earlier. So there should be a way to produce some homology group measuring laxness of F directly, but yeah, we don't know how to do that yet. Thank you.
We have time for one question with a quick answer. Tim.
Sure. Can you hear me?
Honestly, not really, but maybe if someone up front repeats it.
Can you just like the last question you asked about like the moving on to the diagram and like what might happen? Have you just looked at like Lurie's notion of p-Cartesian vibrations? Because I think what you're looking at is like the inner morphisms in these guys.
Okay, great. Thank you. Yeah, I did not think about that.
Okay, let's thank our speaker again.
Thank you.